Hello, students. Looks like Zoom updated. My first time in this new version. We'll see how it goes. So, questions coming in. Well, see, that went well. Perfect right off the bat, right? Okay. Well, those buttons are in different places. Let's see if we can get back to it. All right. So we're going to jump over here to problem 16B. Okay. Our goal is to find the area of the following shaded regions. Got it. So notice what we have is we have a piece of an arc length, right? We have a piece of the circumference, a portion of it. I don't know how much, but let's use that and we'll see what we can do. So let me get a little bit of white space with these new tools. I'm only going to screw that up a couple dozen times. So let's put down what we know. We know that we have an arc length of 20. So arc length is an angle over 360 because it's a fraction of the circumference, 2 pi r. And now let's put in what we know, right? We know the arc length and we know the radius. So the arc length is 20. I don't know the angle. Sorry about that. I don't know that one. Times 2 pi r. Okay. Actually, r, I know what r is. R is 10. So I'll just put 10 in there. Okay. So let's hear. And now I want to get the angle by itself, but let's do a little bit of work first. Notice how there's a 20 on both sides. So let's just divide by 20 on both sides. That's gone. 20 is gone. So now I have 1 is equal to theta times pi divided by 360. So I want to get theta by itself. So multiply by the reciprocal or divide by pi over 360, your choice. So this turns out to be 360 over pi. Now that's the angle. I now know what the angle is. Don't change it. Leave it. Don't round it because now we want to do the area. Well, the area is just saying, well, take a fraction, right? Take a fraction of the area, which is pi r squared. Well, let's plug in what we know. I know theta is this right here. So I get 360 degrees over pi, that whole thing divided by 360, times pi times the radius, and we know the radius is 10 squared, so that's 100. Now take a look, 360 divided by pi, but then I multiply by pi. Those are gone. And 360 divided by 360 gives you 1, so the answer turns out to be 100. Waka waka waka! Kind of a cool problem. Kind of a cool problem. We didn't actually ever compute what the angle was, really, in terms of a decimal number, but we didn't need to. And that's always kind of cool, at least to me. So 16B, let's go 19. Let's see, where is that up the top of the next page? I did one of these in the video. I think it was in the homework video, so I did one of them. So maybe I'll do the other one just to kind of show. Okay, so let's see here. I can't remember which one I did. I think I did this one in the video, so I'll do the other one. So what I want to do is I want to say, okay, here's my diameter of the circle. Okay, and I can choose whatever I want to be this. So maybe I'll just call this length R for the radius, right? Oh, I kind of actually do like that. I do like that because now take a look. Now that square, when you think of it, it's broken up into 4 little triangles. And each little triangle is, because these are perpendicular, is r times r divided by 2. So that's 1/2 base times height, which is r squared over 2. But there's 4 of them. So the area of the square, oops, don't know why I drew a triangle, is equal to 4 times r squared over 2, which is 2r squared. Okay, that's the area of the circle. Sorry, of the square. I even wrote a square there. Okay, now the area of the circle, well, the radius is right here. It's the radius of the circle, so area of the circle is pi r squared. Okay, and so now we need to find in which cases there's a smaller percentage of unoccupied space. So first we can find the occupied space, which would be the area of the square divided by the area of the circle. So 2r squared divided by pi r squared. R squareds go away, and we're left with 2 over pi, which again is about 2/3. Okay, so then the unused space would be 1 minus 2 over pi. And so just get a common denominator. And you get pi minus 2 divided by pi. So pi is about 3. 3 minus 2 is about 1. So this is approximately 1/3 of it is wasted. There you go. If you want the other one, I mean, you should be able to do the second one by yourself, but if you need to, I think I made a video of that one already. Okay, 26. All right, let's jump down to 26. Not on this page. Next page. 26. This might be a good one for GeoGebra. Let's take a look. We'll do a little geometry. And I do need grid lines. Does it let me put grid lines on? Show grid lines. Major grid lines, I guess. Okay, so now if we come back, we need to make a shape that is 3 by 5. Okay. Well, let's see here. And then we need to build this other shape as well. So maybe I can draw that. So this one over here is supposed to be 8. That side right there, see this side on A? That side right there is 3. So I need to go 8, then 3, and over another 5. And then this side of D right here is also 5, it looks like. Yeah, 5 and 5. And then across the bottom, go down 5 and 8. Okay, so let's take a look. Let's see if we can do this. So I'm going to put maybe I'll make some segments. Would that help? Shoot, what was the first one? Go down 5. 1, 2, 3, 4, 5. Okay, there's the 5. And then I want to go over 8 and then down 3. Okay, so from here, go over 1, 2, 3, 4, 5, 6, 7, 8. And then go down from here, go down 3. And then connect that back to the beginning. Okay, now what do I do with the other one here? On this other side, I go in 5 and then up 3. Okay, so we'll make another segment from here. I'll go over 1, 2, 3, 4, 5, and then up 1, 2, 3. Okay, and where does this one connect back to? Oh, just back up to the top. Okay, there we go. And then down over to the other corner. So I think this one goes over from here 5. There we go. And I think it goes like to there. And the other one goes from H to E and from E all the way down. So there we go. There's your picture. Now, if I zoom back far enough, oh, excuse me. If I zoom back far enough, this is where things get kind of fun, at least in my mind. If I zoom back far enough, it definitely looks like a single line. And so if I have a single line, then I just add the areas up. But if you're curious as to what's going on here, take a look. Do you see this? There's a little bit of a space between F and that other line, which is just enough space for, you're going to love this, a pop. And I can work my all the way around. And now you can actually find the area of that polygon. I may have to try to do the algebra. Maybe I'll zoom in a little bit more. There we go. Okay, let me let me get back and do area again now that I'm zoomed in. There we go. Area of that. There we go. Take a look. What is the area of that tiny little sliver? And this is why humans are unfortunately not great at this piece, because we really struggle to see how that little tiny sliver can have exactly as much space as this entire square. But it does. Wait, that's 4. That one's only 1. Oh, because I'm not zoomed in far enough. I had to go in further. I'm sorry about that. I forgot to go into the right size. I was zoomed back at a scale factor of 4. So this one right here. There we go. And now if I go down here, the area here will be 1. So yeah, if you build it double the side lengths, it's 4 times as big, Scott. Good job. So there we go. So this little tiny piece right here, if you shaved off all the horizontal pieces and you put them right in here, they would fill that entire area perfectly. Okay. Now remember, the same thing is true. This concept can be shown in many, many, many different ways. If you have just a point floating on a line and then you have a segment down below, you can make a polygon. And what's great is the area of that polygon, as you look at it, right, is, right, 12.3. But watch, as I pull this point down the line, this remains as long as I stay on the line. I didn't create a parallel line. Let me create a parallel line so I can just avoid this entirely. I'm I'm not able to keep it on the line because I just picked a random point. So let's go and we'll just pick any segment. And then we will pick a a point kind of up here on the line, and then I'll just build a parallel line. Okay. Now just choose any point you want on this new line and build yourself a polygon. Area is 12.5. Now, but if you come up here and you grab this point and you drag it down the line, the area of this shape, even though it's really stretched out, is still 12.5 because it has the same base and it has the same height. So we as humans struggle with that because when you get out here to the very, very, very far ends, you might be thinking, are you kidding me? Look how far it's stretched. There's hardly anything in there. Doesn't even look correct. Are you sure? It just looks like a line, but it still has the same amount of area in it. So that's kind of the big piece there. All right. Very cool. I do like that problem. And it does work with consecutive digits of the Fibonacci sequence. So you could recreate this if you wanted to. This one here is you can notice it's a 3, then a 5, and 3 plus 5 is 8. So it works fine. If you wanted to, you could recreate it with a 5 and 8 and a 13. So 5 plus 8 is 13 if you choose to. Very interesting. The other thing you could kind of say that might help is to go back to what we did earlier in this course and talk about the idea of slope. This to this, I went up 3, I went this direction, or I went down 3, whichever way you want to go. Down 3, and I went right 8. So my ratio here for the B triangle had better be 3 and 8. Well, if this is 3 and 8, right? If that's 3 and 8, then that's fine. That slope still works. But now I have to connect these points, right? I have to. But this is only 5. So this ratio here is right 5 down 2. And I got to tell you, negative 2 over 5 is not the same as negative 3 over 8. So it just doesn't, the slopes don't match up. You can actually graph it to show all the area, but don't forget your technology. Don't forget it. kind of it's your friend. Let's take a look. We got MC number 3. Okay, I'm just going to give a push on this one. Yeah. Just find the areas of the two pizzas. That's what I would probably do, right? If I was selling just a spaghetti noodle or something like that, right? Then I would say however long it is tells me how much I should charge because it's like the thinness is the same. But when you go to like a pizza, right? Let's just say the radius here is 3 and the radius down here is 9. Okay. Well, the area is pi r squared. So the area here is 9 pi. But down here it's pi r squared. So the area here is 81 pi, which means the ratio is 81 pi over 9 pi. Pi's go away and you get 9 or 9 to 1, depending on how you want to write it. So I tripled the radius, but my area is 9 times as big. That's a pretty big difference. Okay, that's my hint, my shove there. Of course, you're doing it with a 10-inch and a 20-inch pizza. And when they say 10 and 20, those are the diameters. I showed you the radius. You'll have to take that step, of course, to find the radius. And MC number 4, let's take a look. Explain how the dissection. I think I did some nudge on this one in the video for the MC, so you can also check that one. But yeah, think about what we were doing in class where we'd kind of cut something and kind of tip it over, or we'd kind of rotate. I think in class we rotated and made this shape, which is great. Nothing wrong with that shape. But you could also take this point and just cut straight across, right? Using the mid segment theorem. So you kind of go to the midpoint of each side, then it has to be parallel to the other base. And that leaves you with a little triangle here, and that triangle has the same angle going down as you started with, so it can actually just kind of swivel right around. And this is what you end up with. Okay. And that's it. Remember, if you're using the midpoints, then all of the linear measures, because the midpoint is halfway, all the linear measures will be the same ratio. So they should be half as big. So the height of the triangle won't be the same anymore. It should be half of the height that you had before. There you go. Okay. Very cool. I think that's it. Let me double check. Yeah, I think that's it for now. So if you have other questions, please let me know. I can meet up with you in Zoom on campus, whatever you need. All right. I'll see you soon. Off you go.